We are now going to start the presentation of the last module, module number 4 of chapter 2. In this module, we are going to introduce the notion of inner measure, which was developed as a dual notion of the notion of outer measure. Now, we will not go into the details of the properties of inner measure, because it is not needed that much in our later chapters. But we need to understand what motivated its introduction. Recall the definition of Riemann integral. You know that for a positive bounded integrable function f defined on closed interval a to b f x dx denotes the area of the undergraph, which is bounded by the curve y is equal to f x, the x axis, and two vertical lines x is equal to a and x is equal to b. Now, in order to calculate that area or the value of the Riemann integral, what we did is that we had taken partitions P of closed interval a b, and we had constructed the upper sum UPF and the lower sum LPF. Now, if we consider the picture, then the lower sum is actually the sum of the areas of finite number of rectangles which are inside the undergraph, and UPF is the sum of areas of finite number of rectangles which are over the undergraph, gives an estimate from the outside. Here we have already seen that while calculating the measure of a set, we have an estimate from outside which is known as Lebesgue outer measure. So, similarly, we can think about an estimate from inside, which we can call the inner measure. So, we start with the definition of outer measure first. See that we can redefine the definition of Lebesgue outer measure of a set E subset of R in the following way. Mu star of E, where star is given on the upper side, is defined as infimum of mu of O, where O is any open set containing E. Now, see that any non-empty set E of real numbers always contains some closed sets, because we know that singleton sets are always closed, finite sets are closed. So, whenever a set is non-empty, it always contains some closed sets. So, we can consider the following definition. For E subset of R, we define the inner measure of E as mu lower star E is equal to supremum of mu f, where f is any closed set contained in E. So, what is the difference between the upper star and lower star, that is the outer measure and inner measure? In the case of outer measure, we are taking open sets containing E, we are taking the measures of those open sets and calculating the infimum of all these numbers. In inner measure, what we are doing is that we are taking closed sets contained in E and taking the measures of these sets, we have a set of real numbers which are intuitively all less or equal to the length of the set E, and we are taking the supremum of all these numbers. Obviously, from the definition of outer measure and inner measure, it is clear that mu lower star E is less or equal to mu upper star E for any E subset of R. Also, it is quite easy to prove that like Lebesgue outer measure, the inner measure is also monotone. That is, if A is subset of B, then mu lower star A is less or equal to mu lower star B. Now, recall this characterization of measurable sets. If a set E of real numbers is given, we had seen that E is measurable if and only if for any given epsilon greater than 0, there is an open set O and a closed set F with the property that F subset of E subset of O such that measure of O minus F, the difference between the open set and the closed set, is less than epsilon. So, now we will prove this important theorem that if E subset of R is such that the Lebesgue outer measure mu upper star E is less than infinity, then the set E is measurable if and only if for the set E both the inner and outer measure are same. We start our proof. First, suppose that the set E is measurable. So, here by measurable we mean the measurability in our earlier sense. Then for epsilon greater than 0, there exists an open set O and a closed set capital F such that F subset of E subset of O, and we have the property mu of O minus F is less than epsilon. But then if we consider the outer measure of E, since E is contained in O, so mu upper star E is less or equal to mu of O, because mu upper star E is the infimum of all possible mu of O, where O is an open set containing E. Again, mu of O is less than mu of F plus epsilon. This is again less or equal to mu lower star E plus epsilon. The logic is that mu lower star E is the supremum of all those numbers mu F, where F are closed sets contained in E. Since this relation is true for any epsilon greater than 0, so we ultimately have mu upper star E is less or equal to mu lower star E. And we already know that the inner measure is always less or equal to the outer measure. So, we must have the inner measure equal to outer measure, that is mu upper star E equal to mu lower star E. So, the condition is necessary. Now, we will show that the condition is also sufficient. So, conversely, suppose that mu upper star E is equal to mu lower star E. Let epsilon greater than 0 be given. Then from the definition of the outer measure and inner measure, we can find an open set O and a closed set capital F such that E is subset of O and mu of O is less than mu upper star E plus epsilon by 2, whereas F is subset of E and mu F is greater than mu lower star E minus epsilon by 2. This implies that mu of O minus F, which is equal to mu O minus mu F, because we have already seen that the Lebesgue measure is subtractive, and by our assumption mu star E is less than infinity. So, F being a subset of E also have finite Lebesgue measure. So, this whole thing is less than epsilon. So, we have mu of O minus F less than epsilon, but see that this is the characterization of measurability. So, we have shown that if for a set E with finite Lebesgue outer measure, the outer measure is equal to the inner measure, then it satisfies the equivalent criteria for measurability, and so E is Lebesgue measurable. Now, one should be careful that this characterization of measurable sets is not generally true for sets for which the outer measure is infinity, and here is the weakness of the notion of inner measure. For example, consider the set E where E is obtained by taking the union of two sets P, where P is the non-measurable subset of closed 0 1 open, which we had constructed in the last module, and closed 2 infinity open. Observe that mu upper star E as well as mu lower star E are both equal to infinity, because I have the set closed to infinity open whose outer and inner measure are both equal to infinity, and it is itself a closed set contained in E. But the set E is not measurable, because if E is measurable, then from the property of measurable sets we already know that if two sets are measurable, then their difference is also measurable. So, E minus closed to infinity open should also be measurable, but this will imply that the set P will also be measurable, which is not possible, because we have taken capital P as the non-measurable subset of closed 0 1 open. So, this set E is not measurable, and this shows that this particular condition cannot be treated as an equivalent condition for the measurability of a set E if the set E has infinite outer measure. We now present a result which is quite interesting. If delta is a bounded open interval containing a set E, then we are going to show that mu upper star E plus mu lower star delta minus E is equal to mu of delta. The proof goes like this: let epsilon greater than 0 be given. Now, from the definition of the inner measure of delta minus E, we can find a closed set F subset of delta minus E, which has the property that mu of F is greater than mu lower star delta minus E minus epsilon. Then G is equal to delta minus F is an open set, because delta is already a bounded open interval and F is a closed set. So, their difference is an open set. And further see that G is equal to delta minus F, this contains delta minus E, which comes as only the set E. So, G is an open set containing the set E. Consequently, using the definition of outer measure of the set E, we have mu upper star E is less or equal to mu of G, but this is equal to mu of delta minus mu of F using the subtractive property of the Lebesgue measure, and this is again less than mu of delta minus mu lower star delta minus E plus epsilon. That is, we have mu upper star E plus mu lower star delta minus E is less than mu delta plus epsilon. Now, see that we have the epsilon only on the right hand side. The left hand side is true for any epsilon greater than 0. So, taking into account that the above inequality is true for any epsilon greater than 0, we get mu upper star E plus mu lower star delta minus E is less or equal to mu delta. We will now prove the reverse inequality. Now, we start from the definition of the outer measure of E. So, from the definition of mu star E, we can find a bounded open set G0 containing E such that mu of G0 is less than mu upper star E plus epsilon by 3. Since delta is a bounded open set, let us write delta as open interval capital A capital B. Now, choose an open interval small a small b with the property that capital A less than small a less than capital A plus epsilon by 3, whereas small b is taken between capital B minus epsilon by 3 and capital B. Now, let us consider this set G, which is equal to delta intersection G0 union two open intervals. One is open capital A small a and open small b capital B. Now, see that we have taken the union of two open intervals and the intersection of two open sets which is again open. So, G is also open. Obviously, then G is an open set containing E, and further measure of G mu G is less or equal to mu G 0 plus the measure of the two intervals which are again less than epsilon by 3 plus epsilon by 3 by the monotonicity of the Lebesgue measure. So, the end product is less than mu upper star E plus epsilon. Now, take capital F equal to delta minus G, which actually comes out as closed interval small a small b minus G. See that G is an open set, closed interval a b is a closed set. So, the difference is again a closed set. So, clearly capital F is a closed set and capital F is subset of delta minus E. And now, using the definition of inner measure, we get mu lower star delta minus E. This is greater or equal to mu of F, which is equal to mu delta minus mu G, because we already know that mu is subtractive, and this is greater or equal to mu of delta minus mu upper star E minus epsilon. And consequently, we get mu upper star E plus mu lower star delta minus E is greater or equal to mu delta minus epsilon. Again, observe that on the left hand side we have a fixed quantity which is greater or equal to the right hand side for any epsilon greater than 0. So, taking into account again that epsilon greater than 0 is arbitrary, we get mu upper star E plus mu lower star delta minus E is greater or equal to mu delta, and this proves now the equality. And in the next result, we will see that we can prove the same theorem by replacing the bounded open interval delta by a more general set, just a measurable set B. We now present our last theorem of this module. If we take a measurable set B and E is a set which is subset of B, then mu lower star E plus mu upper star B minus E is equal to mu B. That is, if we take a measurable set B containing any set E, then the measure of the set B can be obtained as the sum of the inner measure of one part and the outer measure of its complement. We start our proof. See that B is a measurable set and E is a subset of B. We first use the definition of the inner measure of E, that is mu lower star E. Now, by the definition of inner measure, given epsilon greater than 0, we can find a closed set F subset of E such that mu star of E minus F is less than epsilon. And so, if we consider the set F, it is already a subset of E, which is again a subset of B. So, F is a subset of B. Now, we can write B as the union of two disjoint sets F and B minus F, and using the additivity of Lebesgue measure, we have mu B equal to mu F plus mu of B minus F. Now, this is greater than mu lower star E minus epsilon plus mu upper star E B minus E, because see that B minus F is again subset of B minus E. So, we can use the monotone property of Lebesgue outer measure. Now, since epsilon greater than 0 is arbitrary, so we finally get mu B is greater or equal to mu lower star E plus mu upper star B minus E. Thus, we have proved one part of the equality by showing that mu lower star E plus mu upper star B minus E is less or equal to mu B. Now, we will have to show the converse part, that is, we will have to show that mu B is less or equal to mu lower star E plus mu upper star B minus E. So, to prove the reverse inequality, we first note that we can find a G delta set G dash containing B minus E such that mu of G dash is equal to mu upper star B minus E. This follows from the definition of Lebesgue outer measure. Now, set G as G dash intersection B. Obviously, G is a measurable set, because B is already assumed to be a measurable set, and G dash being a G delta set is also measurable, and intersection of two measurable sets is again measurable. Now, see that B minus E is subset of G, this is subset of B, and consequently again by the monotonicity of Lebesgue outer measure, we have mu of G, which is actually equal to mu upper star G. This is equal to mu upper star B minus E. Now, since B minus G is subset of E, so by the monotone property of the inner measure, we have mu lower star B minus G is less or equal to mu lower star E. Consequently, we have mu B equal to mu G plus mu of B minus G, which is equal to mu upper star B minus E plus mu of B minus G, which is less or equal to mu upper star B minus E plus mu lower star E, and we have the reverse inequality. So, combining the two inequalities, we get the desired result. So, to summarize, what we did in this module is that we have defined the notion of inner measure, which is the dual notion of outer measure, and we have seen that for sets with finite Lebesgue outer measure, we can get an equivalent criteria of Lebesgue measurability with respect to this notion. We have actually shown that a set E for which mu star E is less than infinity, it is Lebesgue measurable if and only if mu upper star E is equal to mu lower star E, that is the outer measure of E is equal to the inner measure of E. But the problem with this alternative definition is that this is not suitable for sets for which Lebesgue outer measure is infinity, and we have seen such an example. So, with this we finish this module.